We are moving into our last, third and final unit of material, and we're going to start putting together some ideas here before too long. So you'll notice this section in the notes is called Markov Chain Monte Carlo Techniques. So, in other words, here's that MC you may have heard of before for Markov Chain Monte Carlo. So we're a little bit familiar with Monte Carlo from our Unit 2 material, this idea of random sampling to solve difficult problems. Unit 1, we figured out some different ways to take random samples. Now, the new part is this idea of Markov chains. What are Markov chains and how do they help us use random sampling to solve difficult problems? So we're going to try and piece that together over the next few videos. For now, let's focus on Markov chains. And I apologize in advance, we're going to have a lot of definitions thrown at you in the next couple of pages. So we're going to get a basic feel for Markov chains and definitions and properties of Markov chains, enough of the definitions we need to build up to our important theorem. All right, so the first thing we've seen before is this idea of a stochastic process. We said a stochastic process is just an index collection of random variables, and they're most often indexed by time, t, and all the possible values our random variable can take on is called our state space. Okay, we'll use that same language when we're talking about Markov chains in this section. All right, so I just want to introduce some notation here. When we say something like xt equals I, what we mean is at time t, according to that index, the random variable x takes on a value of little I, takes on value I. Okay, so again, know that notation, x sub t equals I, random variable indexed by time t, takes on value little I. And then I know most of you are familiar with probability notation, but just in case, this notation, probability of A given B, is just telling us to find the probability of event A given some known information, given event B has occurred. Okay, just making sure we're on the same page with the notation before we add more vocabulary. All right, so next important piece of terminology here is this idea of a Markov process. So Markov process is a stochastic process or index collection of random variables, but it has a particular property that needs to be satisfied to be a Markov process. And if you look at our notation here, that property is this idea that our random variable at time t plus 1 takes on value j, or alternatively, if you want to write I sub t plus 1, either one is okay here. So the probability our random variable in the next time step takes on a particular value given its entire history. So this part is our entire history. And if you look at it closely, it makes sense. Our current time step, xt, we're in position I, xt minus 1. Before that, we were in position it minus 1, and so on to xo, that initial starting position. So given the entire history, the probability of going to the next step, some next state, is simply dependent upon where we are now, okay? Xt being in some particular state, it. Okay, so it actually forgets this entire history. Who cares about it? It only depends on where we currently are. So that's kind of in writing here. That is, the process forgets where it's been, and the probability of moving to state j only depends on its current state, not all the other steps it was in. All right, the next bit of important terminology is this idea of a stationary process. We saw that idea a little bit with the Poisson process, where it had stationary increments. Same idea here. The probability of going from state I to state j in one step is the same as going from state I to state J as my first move in the chain for all states and all different time points. In other words, the chances of going from state I to state J has no impact where you are in the chain, where you are in time. Doesn't matter at all. It's going to be the same chances of going from I to J every single time step. Doesn't change. All right, if you put those two things together, if you have the requirement of stationary, your chance of going from I to J at any time point is constant, and 2, a Markov process, where you go next only depends on where you currently are. Forget the rest of your history. If you put those two things together for a stochastic process, you get a Markov chain. Okay, so make sure you know that definition. A Markov chain is a stochastic process, and it needs to satisfy those two properties. Constant probability of transitioning from one state to the next, and the process doesn't depend on your entire history, just your current position. All right, one more bit of vocabulary, and then we'll start looking at examples. The last bit, when we say this is something is a discrete Markov chain, we mean the state space is countable. So maybe I have time steps 1, 2, 3, 4 out to infinity. Okay. So let's look at an example here of a Markov chain. Markov chains are usually defined by two things. They're defined by their initial distribution, and as you'll notice in the notation here, it tells us the probability at time point 0, so our initial position, the initial value of our random variable equaling some state I, is given in this vector A. So for example, suppose I have this vector A, and it takes on value 1/3 for each piece. Notice the vector sums to 1, so have that observation here. So this is telling me I have a Markov chain with 3 states, 1, 2, 3, and I'm equally likely to start off in any of those 3 states. So I'll say equally likely to start in any of the 3 states. The second piece required to define a particular Markov chain is our transition matrix. So this is our matrix that gives the rule, those stationary probabilities, for going from one state to the next. So here's our matrix T for an example. And in this notation, the rows represent our current position. So row I is current position I. And then the columns tell us where we're going. So column J says we're moving to position J. Column J is our next step, where we're going to in the next step. All right, so for example, suppose I wanted to find the probability that at xt plus 1, our random variable takes on value 1, given, I don't care where it's been in history, I only care where we are now. That's the Markov process of this. So xt is equal to 2. So given that at the current time I'm in position 2, so it wants to find the probability of moving to state 1 in the next time step. So in the transition matrix, this is just given by the entry 2, 1 on the matrix. So I'm starting in position 2, and my probability for moving to state 1 is given by my column is 1/2. And also note, we have this observation up here that for example, starting in state 2, my probability for moving into any of the other 3 states, those must sum to 1. So my row sums are always going to be 1. Just to make sure we're good with this, if I'm interested in the probability that, these are bullets here, sorry they don't look like it, xt plus 1 is equal to, I don't know, 2 given xt is equal to 3. That's described in the 3-2 spot on the matrix. So that's telling me I'm currently in position 3, given I'm in state 3, so that's here. The probability of transitioning to state 2 in 1 step would be 1/3. Okay, so hopefully you have a little bit of a sense for our definition for a Markov chain. Again, requires us to have stationary probabilities, Markov process, so forget the entire history, just where you currently are. And to define a Markov chain, we can do that by giving the initial distribution, where we're like the probability of starting in any particular state, and then our transition matrix, our rules for moving from one state to the next. Okay, in the next page, we're going to give some vocabulary that goes along with these ideas. So the first bit of vocabulary is this idea of states being accessible. And state J is said to be accessible from state I if Pij, so that part is not new, we just talked about that, the probability of moving from state I to state J. And let me clarify, this part is new. This little n superscript is telling us we can go from I to J in n steps. So it doesn't have to be one step, but it's possible to go from state I to state J in some number of steps. So I'll just say, so that probability is greater than 0, or in other words, possible to go to J from I in some number of steps n. Okay, we'll talk more about n later on. So the notation we're going to use is this I arrow j to say we can go from state I to state j in some number of steps. That's possible. Again, the vocab word there is accessible. I can get from state I to state j. Now, if that goes both ways, if we can go from I to j and back from j to I, then they're said to communicate. We can go back and forth between the two. I and j communicate, and they have our usual properties of being the relation of being reflexive, symmetric, and transitive. Right, next property or terminology is this idea of a communication class. So if two states communicate with one another, they're said to be part of the same communication class. And it's also interesting to note that our state space is partitioned by communication classes. We'll see what we mean in some following examples. One more vocab word before that. It's this idea of a Markov chain being irreducible. And when we say it's irreducible, we just mean it has one communication class. So if we have one communication class, it means all our states communicate with each other. So I'll just say, i.e., all states communicate. Okay, so if you can get from one state to any other state, doesn't matter, in your particular Markov chain, then that chain is called irreducible. And we're going to require that later on. Okay, so to get some feeling for this, our first example is this irreducible. So this is example we had on the bottom of the previous page. We've got our transition matrix. So let's think about it. Can we get from one state to the next for any of these? Do all states communicate, basically, is what we're asking. So, for example, can I go from state 1 to state 2? Absolutely. I can go from state 1 to state 2, and the probability of that is this entry here, 1/2. Can I go from state 2 back to state 1? So, given I'm in state 2, sure, I can go to state 1. That probability is 1/2. So I can say states 1 and 2 communicate with each other. Okay, what about state 1 and state 3? Can I go from state 1 to state 3? So starting in state 1, going over to state 3, I cannot do that in one step. But remember our definition. Our definition said it doesn't have to be one step. It just says n steps. Some number of steps I can possibly get from state 1 to state 3. So let's look a little more. I could go from state 1 to state 2. That has a probability of 1/2. That can happen. Once I'm in state 2, I can hop over to state 3 with probability 1/4. So it is possible to get from state 1 to state 3, just not in one step. So sure, state 3 is accessible from state 1. What about going the other way? From state 3, can I get back to state 1? So here's state 3. I can not get to state 1 directly in one step. But let's think through it. Can I go in a few steps? So state 3, I could go to state 2, for example. Once I'm in state 2, I can get to state 1. So sure, it does go back the other way. So that means state 1 and state 3 communicate. If you want to pause the video for a moment to think about the other option, 2 and 3, go ahead and do that. Okay, hopefully you've paused and checked it and you found that sure, indeed, you can go from state 2 to state 3 and from state 3 back to state 2. So states 2 and 3 communicate. So we notice here, all of our states communicate with each other. All states communicate. And since all states communicate, that's the definition of irreducible. They're all in the same communication class. So I'll say, therefore, irreducible. All right, let's try another example of this using a new transition matrix. So we have this example. We want to figure out, is this one irreducible? So let's think through this again and figure out what our communication class or classes are. So communication class, one class if it's irreducible. Classes if it's not irreducible and you can't go from any one state to any of the others in some number of steps. So let's start with state 1 and state 2. State 1 can go to state 2 in the next step, probability of 1/2, so sure. And then state 2 can go to state 1 with also probability 1/2, so I'll draw my little arrow here. State 1 and 2 communicate. All right, what about state 1 and 3? So from state 1, I cannot get to state 3 in one step. Can I go through in a few steps? Let's see. I can go from state 1 to 2. Once I'm in 2, can I get to 3? Nope. State 1 only goes to state 2. It doesn't go to 2 or 3 or 4. So I've run out of options. 1 does not communicate with 3. So 3 is not in a communication class with state 1 and 2. Let's check out 4. If I'm in state 4, can I communicate to state 1? Absolutely not. If I'm in state 4, I must go to state 4. That's my only option, probability 1. So states 1 and 2 are in a communication class. State 3 is its own communication class. And state 4 is also in its own communication class. So, is this irreducible? That's a big no. I've partitioned the space by communication, my 3 communication classes here. And they're not all the same. It's not one communication class. It's 3 disjoint communication classes. So not irreducible in this example. Before we move to the next example, let me just comment on state 4. State 4 is called an absorbing state. So any state is called an absorbing state if once you enter that state, you cannot leave. So once I'm in state 4, my only option is to remain in state 4. So once in state 4, we cannot leave state 4. All right, let's add some more vocabulary and continue with the current definitions as well. So next vocab term is the idea of the period of a state. So we had this idea of communication classes being able to go from one state to the next in the communication class in some number of steps. The period of that state is how many steps it takes to go from that state back to itself, the greatest common divisor of all those possible return times. So let's check out an example, and we're going to also denote this transition matrix with a graph. So here's our transition matrix, 0, 1/2, 0, 1/2, and then we'll just kind of alternate that in our structure here. Let's also draw this as a directed graph. So here, sometimes that's a bit easier to read than looking at all this through a matrix. So state 1, here's state 2. So if I'm in state 1 according to the matrix, remember that's indicated by the row I'm in. So if I'm in state 1, I can't go back to state 1 in one step. I can either go to state 2 with probability of 1/2. So I'll draw that direction. Or I can't go to state 3 in one step, but I can go to state 4 with probability 1/2. Oh, I wrote 1/4 here. I was thinking ahead. Sorry. So from state 1, I can either go to state 2 or 4 with probability 1/2. From state 2, I can either go to state 1 with probability 1/2. So from state 2, I can go back to state 1 with probability 1/2, or I can go to state 3 with probability 1/2. From state 3, I'm either going to go back to 2 or 4 with probability 1/2 in either direction. And then if I'm in state 4, I'm either going to go to state 1 or 3, equally likely. All right, so here's a directed graph. Or digraph of how to transition among my 4 states, representing this transition matrix. All right, so we have this idea of a period. So I'm interested in the set of n such that the probability of going from state I back to state I in n steps is greater than 0. So in other words, what are the number of steps it might take me to go from state I back to state I? What's that set? So let's look at state 1, for example. State 1, I could go from state 1 in 2 steps. I could go from state 1 back to state 1 in 2 3, 4 steps. I could go from state 1 to state 1 in 1, 2, 3, 4, 5, 6 steps, 8 steps, and you think about it some more, so on. Okay, so the period of state 1, and I'm keep saying state 1, but I am writing I. Notice how symmetric our graph is. I'm using 1 as an example, but here I apply, it's for all the states here. So this is this observation, if you thought about it, it's for all I, 1, 2, 3, and 4, all those 4 states. Same, I would make the same observation. So the period of I, again, any of those 4, because of this nice symmetric pattern, is going to be 2 for all of these I. Our greatest common divisor of all these return times is 2. Okay. Another side note here, this example is also irreducible. If you want to pause and think about that, go ahead, check it, but we can get from one state to any of the others. They're all in the same communication class, meaning this is irreducible. Okay, almost there for this video. Let's check out just a few more properties and examples. So on the top of the next page, I've started with our directed graph, and let's pause if you want to, pause the video, and try and come up with our transition matrix based on the directed graph. All right, hopefully you've tried that out, and you have something that looks like this. The probability of going from state 1 to state 1, we have this kind of little loop thing. That's going to happen half of the time. The probability of going from state 1 to 2 happens half of the time. And then from state 1, I can't get to state 3 or 4 in one step, so those are 0. Then if I'm talking about state 2, the only place state 2 goes is to state 3, so I'll put a 1 here. The only place state 3 goes is to state 4. And the only place state 4 goes is back to state 1. So hopefully you have a transition matrix that looks something like this. So again, maybe pause and think this through for yourself. Find the period of this, and then also ask, hint, there's one communication class. All I have the same period. So figure out the period. And also think about, do we have any absorbing states here? So pause the video, think about that. All right, hopefully you've thought about that for a moment and concluded that the period is 1 for all I. So you can work your way through all 4 of these different states to come to that conclusion. But for example, starting at state 1, I can return to state 1 in 1 step, in 1, 2, 3, 4 steps. I can go, so the greatest, and so on. I could keep going. The greatest common divisor there is definitely going to be 1, though, because I have this little loop here. And it'll be similar for the other states. I can go from state 2 back to state 2 in 1, 2, 3, 4 steps, or it could be 1, 2, 3, 4, 5 steps, and so on. So the greatest common divisor there will also be 1. Same idea for states 3 and 4. So our period for all the different states is 1. And then that question about absorbing states, we don't have any absorbing states. Hopefully you came to that conclusion. So just because you have a 1 in the row of your transition matrix doesn't mean you have an absorbing state. That 1 specifically must be in the main diagonal. So in our last example, we had a 1 in this bottom corner, meaning if I was in state 4, I had to stay in state 4. But here, if I'm in state 4, I can get out of state 4. I'm going to state 1. So we have no absorbing states. Okay. So I'll make that observation. To have an absorbing state, we need a 1 on the main diagonal of our transition matrix. All right, last definition before we take a break here. So we're not going to prove this one, but the period of a state is in fact a class property. So if you have two states communicating or they're in the same communication class, then their periods are also going to be the same. Another definition, if di is 1, the period of a state is 1, then that communication class is said to be aperiodic. Okay, we're going to need some of these things later on as well. Irreducible, aperiodic, tuck all these definitions away. So last example before our break. First, let's draw a directed graph of this transition matrix, find our communicating classes, and find the period of each of these communicating classes. If you want to pause it and give that a try, go for it. All right, hopefully you've tried it. Let's check out our directed graph first. So state 1 we have here. And according to our transition matrix, from state 1, I can either go return to state 1 half the time or move on to state 2 half the time. So I'll draw one of these little loops here. I can go back to state 1 half the time, or I can go to state 2 the other half of the time. Okay, from state 2, I can go from back to state 1 half the time, or I can stay in state 2 the other half of the time. So I'll draw another one of those little loops. Then, if I'm in state 3, I'm going to go to any of the 4 states with equal probability. So I could go to state 2 half the time, state 1 half the time, return to itself. Oh, I'm saying half. These should all be 1/4. There we go. Fancy 4. Or I could go to state 4, a fourth of the time. All right, then once I'm in state 4, I can't go anywhere else. That was that absorbing state. I'm stuck in state 4 forever. Thinking of Sandlot, the movie there, forever. All right, so let's figure out our communicating classes. We did this previously in our example. We found states 1 and 2 communicated. State 3 was in its own class, and our absorbing state 4 was in its own class. And if you work through thinking about the period of these guys, hopefully you found that these are aperiodic. Our period for state I is 1 for all 4 of our states. So i.e. all aperiodic. All right, let's take a break here and we'll get into our next set of definitions leading up to the really important theorem we need for our MCMC techniques.